Welcome to A-Level and AP Physics, a place where you can improve your understanding of physics with confidence. In today's class, we will discuss first law of thermodynamics, and in this class, I will explain you how to use first law of thermodynamics to answer past paper questions from Cambridge A2 Physics. Part A is simply asking us what is meant by the internal energy of a system. First of all, let me explain to you this in detail, what is internal energy of a system, and then we will write down a proper answer for this question. It simply is the sum of kinetic energies plus sum of potential energies of all the molecules. Now, kinetic energy, when we talk about kinetic energy is simply due to motion of molecules, and motion of molecules we can describe with the help of speed of molecules. If the molecule speed is greater, it simply means that kinetic energy is higher. And if the speed is lower, kinetic energy will be lower. And kinetic energy of molecules we can also judge by the temperature of the system. If temperature of the system is higher, it means kinetic energy of molecules is higher. And when we talk about kinetic energy of molecules, we are not only talking about translational motion of molecules, we also talk about translational motion, vibrational and rotational motion of molecules. Now, let's move on to potential energy now. Potential energy is due to intermolecular forces. And potential energy of molecules, it depends on separation between molecules, and also it depends on bonds between molecules. If the separation between molecules is greater, potential energy will be higher. And if separation between molecules is small, potential energy also will be lower. Now, what does it mean by bonds? How potential energy depends on bonds? If the bonds are broken, for example, when liquid change into gas, potential energy of molecules increases. And if bonds are formed, potential energy of molecules decreases, means when gas change into liquid. So this is what we need to understand about potential energy and kinetic energy. For ideal gases, we need to understand there are no intermolecular forces between ideal gases, means between ideal gas molecules. Our assumption, this is what assumption we make for ideal gases, that there are no intermolecular forces. As there are no intermolecular forces, it simply means that there is no potential energy. So ideal gases, they don't have potential energy. So if no potential energy, it simply means that for ideal gases, their internal energy is simply equal to kinetic energy of molecules, or we can simply say is equal to sum of kinetic energies of all the molecules. Now let's try to define what is internal energy of a system. I hope you have clear idea now what is internal energy of a system. Let me explain to you how to write a proper answer for this question. This is how you can write down internal energy of a system. So as I have explained to you, that it is the sum of all the random and microscopic potential energy and kinetic energy of all the molecules in the body or in the system. Why we call random? It means molecules, they do not have the same speed. All molecules, the speeds are different, and the separation between molecules is also different. That's the reason we said random distribution. For part B, it is given to us that an ideal gas undergoes a cycle of changes as shown in figure 2.1. So this is given to us that this is an ideal gas. For ideal gas, we simply need to understand that internal energy, or simply we can say change in internal energy, is equal to change in kinetic energy. energy. Because ideal gases, there are no intermolecular forces between molecules, so they don't have potential energies. So this is very important point. Ideal gas is given to us. Now it is also given to us that it complete one cycle. So from P then goes to Q, then R, then to P. If you read question, you can also see here that at constant volume, 97 joules of thermal energy is transferred to the gas. So constant volume, if you look at between P and Q, volume is constant and volume is equal to 950 cubic centimeters. So here there is no change in volume. We can also say there is no work done on the gas or by the gas, because work done is equal to P times delta V. So there is no work done. So this is very important point. We can also write down here there is no work done. Now let's move on to question now and try to answer first question. Part B1 is simply asking us state the total change in internal energy of the gas during complete cycle PQRS. So this is our complete cycle, as you can see from here. So this is complete cycle. Explain your answer, and this question has 2 marks. First thing what we need to understand is that, as I already mentioned, we are talking about ideal gas in this case. For ideal gases, the total change in internal energy is equal to total change in kinetic energy. And the kinetic energy of gas, it depends on temperature. So we can simply write down the change in kinetic energy. This is depending on change in temperature. If there is no change in temperature, it simply means that there is no change in kinetic energy of molecules, or simply we can say the change in internal energy, this is equal to 0. So this is main concept we need to understand. So if you look at this complete cycle, you can see at point P, initial temperature Ti, this is equal to 280 Kelvin, and T final is also equal to 280 Kelvin, because this is one complete cycle. At the same point, there is only one temperature. So in this case, we can simply say Ti is equal to Tf, or we can simply say in this case delta T is equal to 0. So it simply means that there is no change in temperature, so there is no change in internal energy. So this is simply we need to write down. So we can say that Ti is equal to Tf. So there is no change in temperature. So when there is no change in temperature, it means there is no change in kinetic energy. So finally we can say there is no change in internal energy. Here is answer. You can also write down your answer like this. You can say as final temperature is equal to initial temperature, so no change in internal energy. Now let's move on to second part now, part B2. Let's try to answer this. For part B2, we need to understand how to use first law of thermodynamics, means delta U is equal to Q plus W. And W, this is work done on gas. We simply need to understand how to use first law of thermodynamics for second part. Now, for change P to Q, as you can see here, from P to Q. So Q is here. Now, as you can see, in this case, there is no change in volume. As I mentioned before, in this case, delta V is equal to 0. It simply means that P times delta V is equal to 0, or we can simply say work done is equal to 0. So we can simply say work done is equal to 0. Now, question is asking us increase in internal energy of gas. So simply you can write down here, as in this case 97 joules of energy is added and there is no work done on gas, so the change in internal energy is also equal to 97 joules. So simply we can write down this is 97.0 joules. For change from Q to R, it is given to us that Q is equal to 0 and W is given to us, that is equal to minus 42.5, means negative 42.5, and increase in internal energy we need to find out. So it's very straightforward one. Simply we can say Q is equal to 0 in this case, and work done on gas, this is negative 42.5 joules. So delta U is simply equal to negative 42.5 joules. So we can simply say that this is negative 42.5 joules. For change from R to P, only work done on gas is given to us. We don't know what is value of Q, and also we don't know what is the change in internal energy. First of all, let's try to write down first law of thermodynamics. Delta U is equal to Q plus W work done on gas. Now for this process, it is given to us that work done on gas, that is equal to 37.0 joules, and we don't know what is value of delta U. So first of all, we need to find out value of delta U, or we need to find value of Q, and then we can find out the value of remaining quantity. So this part is little tricky one and often confusing for many students. So the best way is to find out delta U first. The delta U is quite straightforward one. If we simply understand, for any cyclic process, for any cycle, or simply you can say for any cyclic process, delta U is always equal to 0. So we can simply write down for any cyclic process, means for any cycle, delta U is always equal to 0. Now this is our complete cycle from P to Q to R and to P. So this is complete cycle. So for this complete cycle, we can write down delta U has to be equal to 0, and delta U we already have from P to Q. So this is delta U from P to Q. Then we can also add delta U from Q to R, plus we can add delta U from R to P, and this has to be equal to 0. So as you can see, delta U from P to Q, that is given, that is equal to 97.0, and this is plus, and from Q to R, that is 42.5, and this all has to be equal to 0, because this is one complete cycle. P, Q, R, P, this is one complete cycle. So we can write down delta U from R to P. So if we just solve this one, or delta U from R to P, that will be equal to minus 54.5 joules. So this is negative, so we can simply write down delta U in this case is negative 54.5. We can also write here this is negative 54.5. Now you can see here we have delta U, we have value of W, so simply we need to find out what is value of Q. So if we solve this one for Q, our answer will be negative 91.5 joules. So this much energy is transferred. Welcome to A-Level and AP Physics, a place where you can improve your understanding of physics with confidence. In today's class, we will talk about first law of thermodynamics, and then we will apply this law to solve past paper questions from Cambridge A2 Physics. For this question, it is given to us that the first law of thermodynamics can be represented by the expression, and you can see expression is given here. Part A is simply asking us, we need to state what is meant by the symbols in the expression. Simply we need to explain these symbols. Delta U, let's try to understand first of all what delta U is telling us. Delta U simply represent change in internal energy. When internal energy of the system increase, let's say internal energy of the system increase, then we use positive sign in front of delta U. And when internal energy of the system decrease, we use negative sign in front of delta U. Now let's try to understand what Q is telling us. Q is thermal energy. When thermal energy is added to the system, we use plus sign in front of Q, and when thermal energy is removed from the system, we use negative sign in front of Q. Let's try to understand W now. W represents work done. Work done is positive if work is done on system. So we use plus sign in front of W, and if work is done by system, we use negative sign in front of W. Work done on system, we can also understand if a gas is compressed, then work done is positive. On other hand, if the gas expand, work done on system is negative. So this is all what we need to understand about these symbols. If we have understanding of these symbols now, then we can simply write down our answer for part A. Now as you can see here, delta U is asking us, the question is asking us what is delta U, and this is positive. It simply means increase in internal energy. Now the next one is plus Q. It simply means when heat energy is transferred to the system, and del plus W is telling us when work is done on the system. Let me show you the answer. This is how you can write your answer for this question. For part B1, question is telling us that during the change from A to B, as you can see here, A is here and B is here. During this change means from A to B, it is also given to us that the amount of energy supplied to the gas by heating is 442 joules. As this energy is supplied, it simply means that energy has been added to the system. So simply we can say this is plus Q. Question is asking us, we need to use first law of thermodynamics and we need to show that internal energy of the gas increases by 265 joules. Increases. It simply means that delta U has to be positive. As this question is asking us, we need to use first law of thermodynamics. Let's write down equation for this law. Delta U is equal to Q plus W, and value of Q is given to us in the question. As you can see here, this is 442 joules and this is positive because heat is supplied to the system. So simply we can write down this is 442 joules, but value of W is not given to us, but we can calculate from this figure 2.1. We simply understand work is equal to work done by gas is simply equal to P times delta V. And if we look at this point A, at this point value of P is given, and if we go from A to B, value of P is not changing, means P is constant, and value of P is equal to 5.2 times 10 to 5. Simply we can write down this is 5.2 times 10 to 5. Next we need to find out value of delta V, and value of V at point B, this is 5.0, and value of V at point A, this is 1.6, and we need to multiply with 10 to negative 4, as you can see here. If we simply multiply and solve this one, this is our answer. So this is value of W. But now we need to find out, is this value is work done is positive or work done is negative. If go from A to B, you can see the volume is increasing. It simply means that the gas expands. When gas expands, it means work is done by gas. work is done by gas, and work done by gas is taken as negative. So simply we need to plug in here 177. If we solve this one, our final answer will be 265 joules, and this is the change in internal energy. As this answer is positive, so this is the increase in internal energy. This is what question was asking us. We need to show that the increase in internal energy is 265 joules. For this part, it is given to us that during the change from B to C, internal energy of the gas decreases by this amount. We need to consider energy of molecules, and we need to state and explain the change, if any, in the temperature of the gas. So the first thing we need to understand is that as we are talking about ideal gas, and for ideal gases, potential energy of molecules is equal to 0. So this is the first point we need to understand. Now the second thing what we need to understand is that as we are talking about ideal gas, so it means the internal energy of the gas is simply depending on kinetic energy of molecules. As it is given to us that internal energy of gas decreases, it simply means that kinetic energy of molecules decreases. And if kinetic energy of molecules decrease, it means temperature of the gas will also decrease. So this is what we need to understand. Now if we have understanding of this one, then we can write down our final answer. So this is how you can write down your answer. So the first point we have mentioned, no molecular potential energy. Second, internal energy decreases, so kinetic energy of molecules decreases. As kinetic energy of molecules decreases, so temperature of the gas decreases. For third part, simply we need to consider the change from C to A, and we need to use data from B1 and B2 to calculate the change in internal energy. This is based on one very important concept. Let me explain to you that concept first, and then we will answer this question. Concept is very simple, that in any closed cycle, delta U is equal to 0. Now, if you look at this PV diagram, you can see if I go from A to B, then from B to C, and then from C to A, so this will form a closed cycle. So this is our closed cycle. We can simply write down for this closed cycle the total change delta U. We can simply say delta U from A to B plus delta U from B to C plus delta U from C to A. This has to be equal to 0. In part B1, we have already calculated delta U from A to B, and that was 265. From B to C, it is given to us here, so and this is negative because internal energy decreases, so we can plug in this value. And for this question, we need to calculate delta U from C to A. Now if we simply solve this one, we will get delta U from C to A means the change in internal energy. This is equal to 48 joules, and this is our answer. For the last part, it is given to us that temperature of the gas at point A is 227 degrees Celsius, and we need to calculate the number of molecules in the gas. Now, if you look at this PV diagram, at point A, we can read the value of P from y-axis, and value of volume of the gas we can read from x-axis. Let's write down first of all what is given to us. In this case, temperature is given to us, that is 227 degrees Celsius, and value of P we can simply read from y-axis, and that is 5.2 times 10 to 5 Pascal, and volume we can just read from x-axis, and value of volume is 1.6 times 10 to negative 4 cubic meters. Question is simply asking us, we need to find the number of molecules. We can also write down here. As we know, in this question we are talking about ideal gas, and for any ideal gas, PV is equal to NK2. T. As you can see here, we need to find out value of N, but we have value of P, we have value of V, we also have value of T, and K is a constant. We can find out value of this one from data table, so this is constant. But one thing we need to be careful, temperature must be in Kelvin, and then we simply need to use the formula to find value of N. This is how you can do calculations. You can see this is value of P, this is P, and this is value of V, and this is over K, means this is constant, and this is how we have converted temperature in kelvins. Then just simply you need to plug in values in your calculator and you can find value of N, means you can calculate number of molecules.